now that we know what vectors are, at least we have a little bit of an understanding to it, what we're going to do is see what we can do with these vectors, these new quantities that we have. And today, all we're going to do is take a look at adding and subtracting. How do we add and subtract these geometric vectors, and what does that actually mean, okay, to do? So what we do is basically we're starting with we said, yes, the last lesson, we looked at both the quadratic, okay, and also a rectangle, and we used a mapping from one to the other. Well, what we're going to do is we're going to take a look at this displacement, okay, AC, and you see that's the dashed arrow, all right, and it is basically the result of two or more displacements. So in other words, what we have here is AC could be considered going through from point A to point B, and from point B, then we take the vector up to C, okay? So we have the vector AB plus an additional vector BC, and our resultant vector is going to be AC. So the answer to a vector addition question is a resultant vector. All right, and this is what we're going to be taking a look at. Now, what we call this is the triangle law of vector addition because quite simply it forms a triangle. Okay, there's another one that's called the parallelogram law of vector addition, which is pretty much the same thing. It has to be because it's describing the exact same operation, addition. And it's because it was called parallelogram law because it will form a parallelogram. Okay, so here's what we're saying with the law of vector addition. Okay, if we have two vectors, all right, vector A and vector B, what we do to add them together is we arrange them head to tail. Okay, the head of the first, the tail of the second. So A and B, you can see that here's the first A. All right, we've got the tail, all right, here, and it goes to the head there. That's vector A. We line up B at its tail with the head of A. Okay, so it's head to tail, and we end up with the head of B over there. The sum, vector A plus vector B, is nothing more than just simply going from the tail of A, all right, to the head of B. That is the addition, the A plus B. That is the resultant vector. All right. So we line them up. So what I want you to do is when you take a look at this example, you can, what we're going to do is prove the commutative law of addition for vector addition. All right. The commutative law is basically saying that if we take two vectors and we have A plus B, and the same two vectors and line them up B plus A, we are going to end up with the exact same vector. That means it'll have the same direction and the same magnitude. Okay, so here's a simple way of doing this. We've got the grid paper, all right. If we take vector A, for example, and here's vector A, we'll just draw this out, any old vector, and we apply a vector B to it. Let's just say we've got vector B that comes off on an angle. There's vector B. They're already lined up head to tail, okay, head to tail. That means that this vector here that's dashed is the resultant vector, and this is the A plus B vector, okay? Now, how do we then take a look at the A plus B and see if we can switch it around and go B plus A? Well, in this case, we'd have to start with B. So I'm going to move my vector B that I've got on the right-hand side of this diagram, and I'm going to place it basically at the tail of where A was and say that no, now it is vector B. So I'm going to put vector B up, and I'm just going to draw this freehand, okay? So it's going to come through like this. All right. And when I draw it up, we're just going to imagine that this vector B here is the exact same vector B as before. And I'm going to take vector A from the bottom and I'm going to place it up on top. Okay, the diagram that way. And when you do that, and you can imagine this being done with any vector, then you can see that the dashed line then becomes vector B plus vector A when it's designed that way, right? So you have that. And any two vectors can be set up this way. You form the parallelogram, right? Because you see the sides, they have to be the same length, right? The opposite sides are the same length. You know that these ones are vectors, so they go in the same direction. They're parallel as well, and the same length. You see a parallelogram, okay? This is also why the parallelogram law of vector addition holds true as well, okay? I'm going to put this down. So the parallelogram law of vector addition. All right. Basically, this is an illustration of this law as well. And since it's already there, it's a great proof of the commutative law of addition. It's also a great illustration of the parallelogram law of vector addition as well. So the reason why you may be using this, or you may have used this in physics class as well, is that when you get two forces acting on an object, let's say the object itself is here, okay, at the where the two tails are basically for A and B on the left-hand bottom side, all right, they act on this point object here, point mass, and you see them going off in the directions of A and B, these A and B here. Well, what you can do for the addition of this is you basically complete the parallelogram with the top A and the side right B, okay? And you draw your resultant from the two tails all the way across to the two heads, okay? And then you can use um, things like the sine law, the cosine law, all right. If we've got a right triangle, for example, we use all of our primary trig ratios. So you can do the sine theta, you can do cosine theta, tan theta, depending on what angle you want. You can use the Pythagorean theorem, okay, in order to come up with the magnitude of your triangles, okay, the length there. As an example of this, if we take a look at, well, we did this, we did that. The only thing I didn't do is this opposite vector, but I'll do the example first and then I'll come back to the zero vector, okay? When we talk about all using the Pythagorean theorem and all the rest of it, it's because we're forming triangles here. Whenever you have the triangles, you can get the lengths and the angles using the trig ratios that we have and the different laws, okay? So for a quick example, we've got a boat with a velocity of 14 meters per second due north is traveling across a river with a current of 5 meters per second due east. Find the resultant velocity of the boat, all with respect to the shore. Well, if you've got your boat, you're going to draw, again, your geometric vector due north, right? We know that the magnitude is 14 meters per second, okay? When we go east, the current is traveling east and it's smaller, obviously, than the 14. We have the 5 meters per second there. All right. The actual boat itself, with respect to the shore, is traveling somewhat on this diagonal line there. All right. And so what we have to do is we have to find the magnitude, and then we also have to find the direction itself. Okay. Now, when you see, I've already got obviously the answers here, but how we get the answers, you can find the magnitude of the resultant vector by using the Pythagorean theorem and solving for the magnitude of r. Okay. You could also at this point find this theta, okay, in there from tan theta, opposite over adjacent. Okay, so remember, try to go through all of your laws and the sine, cos, and tan to work through this. All right. So if you say, when you go through this one here, you'll notice that I've got that it's 70.35 degrees off the initial shoreline. So we're saying that the shoreline is here. So we're looking at probably that it would be the 70.35, right? Okay, so when you go through your numbers, you'll see that. We'll go through how to determine or how to write down direction You could do it this way. We could say, well, since they're using east and north and east here, we could say that it's probably, the 14.87 meters per second. And then in our square brackets, we can put, well, we're going to start north and we're going to be traveling approximately 29.65 degrees towards the east. Okay, written like this, you can see that we're starting north. Okay, we're traveling towards the east in that direction. Okay, so when you find the theta, you can fit it in specifically right between the north and the east. Okay, let's go back up to what that zero vector was. All right, so when we have our adding an opposite vector, if we have, let's say for example, this vector, we'll call this vector B here, you can see that it's got specific length to it. Direction is east in this case. Well, if we add the negative B to it, and again, remember when we add, we're going to go from the head of the first vector, which is the B vector B, okay? And then we're going to go all the way back, and you can see that we're going to end up, when we lay these on top of each other, we're going to end up back at the initial point that we started. So any vector plus its opposite vector is going to end up what we call, it's got zero magnitude, all right? But to keep it as a vector, we say it's a zero vector. It has any direction, all direction, no direction. It has any direction we want to put it, but there's no specific direction to it, okay? So that is what the zero vector is. You can take a look at it, okay, basically right here in your OneNote section to understand it maybe a little bit better. These are, they're placed on top of each other, okay? So we have the commutative law of addition, we have triangle law of addition, parallelogram law of addition, the zero vector, okay? Basically, the zero vector is designed so that when we add two vectors, we will always get a vector, okay? And now what we do is we take a look at, well, what is subtraction? What is the opposite, right? Vector subtraction, okay, is the opposite operation from vector addition, all right? It's set up the same way as scalar addition and subtraction are. They're opposites. If we take a look at this diagram that we have, you can see that we are adding a specific vector. In this case, we're going to be adding the a minus b vector, okay, to b in order to obtain this a, which is kind of backwards when we see roundabout way. But if we look at the adding of from OB down B to A, okay, you can see you end up with the resultant vector OA. Well, if we want to describe what the subtraction actually is, you can see that if we're starting with vector A first and then we subtract vector B, well, the first vector and the second vector are lined up both at their tails. Okay, that's how we do the vector subtraction. You line them up at the tails. Then, excuse me, the subtraction is starting at the head of the second vector, the head of the second vector, going towards the head of the first vector. And what I mean by the first and the second vector here is the ones listed. A is the first vector listed, then we have B is the second vector listed. So we go from the head of the second to the head of the first. All right. If you look at, the rest of this coming down here, these equations that we have based on vector addition, you can see that, well, first of all, we're proving that substitution works, okay, for vectors, all right? And the other thing that we're proving here, when we take a look at, and it's got equation 1 and equation 2 here, I just started off, by definition, we have vector BA is vector A minus vector B, all right? Working through the triangle here, we also have that vector BA is also A minus or A plus the negative vector b. So we can see that vector addition, all right, we can subtract two vectors by adding the opposite vector. All right, so a minus b is equal to a plus negative b, which is identical to scalar subtraction as well. And what I mean by that is, if you were saying 5 minus 8, that is the same as 5 plus negative 8. So vector subtraction works the same way. All right, that's basically all we're doing. We're taking a look and seeing, okay, here's our new field of study, vectors. What can we do with it that we know we can do with other fields like scalar quantities? And we're just looked at today, adding and subtracting. Okay, so this precise definition of vector subtraction, you can read that through here. Okay, we've got what it is. Remember, when we are adding two vectors, especially geometric vectors, we are going to line the two vectors up tail to tail. All right, and if I were to say that this is vector A and this is vector B here, and we want to know what is vector A minus vector B, remember, we start the head of the second to the head of the first. Okay, so this is our A minus B. All right, so remember that, that's key. Now what I want you to do in this case is take a look, express each of these as a single vector. All right, you can pause and then I'll talk through it after you start again. All right, or you can just follow along. All right, so vector CD, all right, vector CD minus vector CB. Notice they're already lined up tail to tail, which is fantastic. So that means we go from the head of the first, which is B, to the head of the head of the second, which is B, to the head of the first, which is D. So this is simply vector BD. Okay. When we take a look at the second one, we have vector AC. So vector AC is right there, minus vector DC. DC is this here. Well, these are lined up head to head. We don't have that. We don't know that, okay, or what that is. So here's what we do. We can use AC plus negative DC, right? That would be equal to vector AC plus vector CD. Since this is vector addition, we go from the tail of the first to the head of the second. So we have AD. So this is simply vector AD. Okay? So what I'd like you to do is take a look at the homework assigned in this one. They're assigned basically on the VLE. And you can go through that and we can talk about that in the next lesson.